The different combinations of allowed quantum numbers are basically the available orbitals or seats that the electrons are allowed to occupy within the atom. The order of distributing electrons on these available orbitals or available seats in the atom, or if you want, you can call it the seating chart inside the atom, is the electron configuration. And as we discussed in the previous video, we represent the available orbitals with the following notation, where the coefficient here stands for the energy level or the principal quantum number n to which this orbital belongs, and the symbol according to the angular momentum quantum number or the secondary quantum number L, and the different shapes of orbitals based on the value of L. And the superscript here is the number of electrons occupying a certain orbital or a subshell. So writing a configuration or an orbital diagram for an atom is basically writing down the order of the available orbitals and the occupants of these orbitals with electrons. There are two ways to do this. For a hydrogen atom, for example, you can either use the written configuration according to this notation right here, or you can basically represent each orbital as a box and each electron inside this orbital as an arrow. The general rule that determines the distribution of electrons within the available orbitals is basically energy. Available orbitals are basically just seats within the atom or spaces within the atom where the electrons can occupy. The electron will always prefer to occupy the lower energy orbital first. Up till now, we considered the energy of all orbitals that belong to the same energy level to be equal, and is determined by only the principal quantum number n. However, this is actually a mistake because it ignores a couple of other factors that affect the relative energies of these orbitals with respect to each other. And this is what we will discuss next to decide the relative order of energy of these orbitals. So the important factor that Bohr model just ignores is the fact that these electrons are bearing the same charge. So they are gonna encounter repulsion between each other. So taking into account these repulsions is gonna significantly affect the energies of the orbitals. The main effect in this regard is called the screening or shielding effect. How much attraction does an electron feel in the atom? So if we start with the simplest atom possible, which is a hydrogen atom, you will have a 1 plus nucleus, and you will have 1 minus electron. That 1 minus electron is going to be feeling a +1 positive charge, the whole +1 positive charge of the nucleus in this case. And its energy is going to be this value right here, based on the Coulombic attraction that it feels from the +1 positive charge. If you go to a helium plus ion, the energy of the energy level goes to much, much lower value, indicating a much higher attraction, because simply the electron is feeling more plus charges from the nucleus. So that means more attraction, much lower energy, as you can see from the ionization value for that electron here. If you go to a helium atom, where you now have 2 electrons, you can have 2 possibilities here. The first one is that basically each one of these electrons is feeling 1 plus charge from the 2 plus charges in the nucleus, and in this case it should have an energy that equals to the hydrogen atom situation, with 2.18 O2 joule. But you can probably think that it's possible that both of them is actually feeling the whole 2 plus charges of the nucleus. And in this case, it should have had the same energy of the plus ion with negative 8.72 O2 joules. However, the value of the orbital energy in this case is actually something in between, which means the electron, each one of these electrons is feeling somehow greater charge than plus one, but still lower charge than plus two. And that phenomena here is called the shielding. It's basically that each one of these electrons is shielding the other electron from seeing the whole 2 plus charge of the nucleus. Each one of these electrons is going to be feeling what we call an effective nuclear charge that is slightly smaller than the actual nuclear charge based on how efficient the other electron is shielding. So for the lithium case, we have a 3 plus nuclear charge, and then we have two electrons in energy level 1, and then we have one electron in energy level 2. The two electrons in energy level 1 are effectively shielding 2 plus of the nuclear charges and leaving behind just 1 plus charge for the external electron to feel. And as a result, the external electron in the energy level 2 is going to feel a plus 1 charge at a much larger distance in comparison to the hydrogen case, for example. So it's going to have a much lower Coulombic attraction value as reflected by the energy of the orbital right here. It's basically more than 50% less than the energy of the hydrogen orbital. Much less value for the orbital energy in case of lithium 2s orbital in comparison to the hydrogen orbital reflects the fact that it feels much less nuclear charge at much higher distance. So that makes the attraction force much weaker, or the Coulombic attraction energy much smaller. This shielding or screening effect of any given electron by the other electrons in the atom is going to depend on the nature of the orbital that it resides in. And that's based on a phenomenon called the penetration effect of the orbitals. For example, if we compare the attraction that an electron in 2s orbital feels in comparison to the attraction that an electron in a 2p orbital feels, we can clearly see that the 2s orbital has a smaller loop of high electron density closer to the nucleus. So it's said to penetrate the 1s orbital further and more than the 2p orbital. As a result, 2s orbital electrons are going to be feeling much more effective charge or much more attraction from the nucleus than 2p. So it's actually screened less than the 2p orbital. And in general, the screening that the s orbital feels is much smaller than the screening that a p orbital feels, which is much smaller than the screening that a d orbital feels. And as a result, the energy of the s orbital is going to be feeling more attraction, so it's going to have much more negative energy in comparison to the p orbital, which has much more negative or lower energy in comparison to a d orbital. So orbitals that belong to the same energy level are not equal in energy. They will have different energies because they feel uh, different degrees of shielding or screening from the nucleus charge. So as a result of that, as you can see, the energy diagram is no longer having all orbitals of the same energy level with the same energy. We will have slight differences between the orbitals because of the different shielding that each one of them feels. You can clearly see that 2s, since it's shielded less, is going to feel more attraction, so it's going to have lower energy in comparison to 2b. And it becomes much more pronounced effect to the extent that it can sometimes have an orbital that belongs to a higher energy level at a smaller energy in comparison to another orbital that belongs to a lower energy level. And as we said, the electron always prefers to reside in the lowest energy orbital first. So when you start putting electrons in these orbitals, you will basically start with the lowest energy orbital and go to the next one, according to the energies, which again are affected by this penetration shielding effects that we just discussed. So that's the first rule. It's called the build-up or Aufbau principle, is that electrons are always preferring lower energy orbitals first. And based on that, we will find that the order of distributing electrons on the available orbitals is going to be different than the energy level order. So we will start with 1s and then follow this arrow. So it's going to be 1s, 2s, then 2p, and then 3s, 3p, and then 4s, which is going to come before filling 3d. Again, that's just a reflection of the fact that 4s is lower in energy than 3d. And then we will go to 4p, then 5s before 4d, because it's lower in energy, and then 4d, 5p, then 6s, again before even 4f, and 5d, and then 6p again, and then 7s, and so on. Second rule in determining the electron configuration or the distribution of electrons inside the atom is called Pauli exclusion principle. In general, any single orbital can accommodate up to 2 electrons. But how these 2 electrons are distributed with respect to each other depends on Pauli exclusion principle, which simply states that any 2 electrons in any atom cannot have the same set of quantum numbers. So if we consider 2 electrons in one s orbital, for example, the principal quantum number is 1 for electron 1, and it's 1 for electron 2 as well. The L quantum number is 0 for electron 1, and it's 0 for electron 2. And the magnetic quantum number is 0 for electron 1, and it's 0 for electron 2. Exactly identical set of these 3 quantum numbers. This is why it was very important to have a 4th quantum number that is able to differentiate between these 2 electrons to allow them to stay in the same orbital together. And that quantum number is the spin quantum number. It's related to the spin motion of the electron, how the electron spins around itself, either clockwise or counterclockwise. And that type of spinning motion is responsible for the magnetic moment of the electron. So depending on the direction of the spin, the electron will either have a magnetic moment up or down. It has 2 states corresponding to 2 possible values of the spin quantum number, plus 1/2 for the spin up and minus 1/2 for the spin down. So that's the fourth quantum number for any electron, which is the spin quantum number. And as you can see, we will have two possibilities for these two electrons in one orbital. They will either have the same spin direction, and in this case, both of them will have plus 1/2 spin quantum number. That's clearly is in violation to Pauli exclusion principle, because it will result in two electrons that have exactly the same set of quantum numbers. And then we have the second option where one of them is going to be spinning up and the second one is going to be spinning down. And it's clear that this will lead to the same set of quantum numbers here, but it's going to lead to a plus 1/2 value for the spin quantum number for one of them and minus 1/2 value for the second one, which is going to be satisfying Pauli exclusion principle. And the reason why this is the only allowed coexistence of two electrons in the same orbital is that it actually helps to overcome the expected Coulombic repulsion between the two electrons with the magnetic attractions that will take place when you have the magnetic moments in opposite directions. The third rule that controls how we distribute electrons in any atom is called Hund's rule, and it basically states that unpaired electrons will have lower energy. The overarching rule is that electrons always prefer lower energy configurations. Unpaired electrons have lower energy configurations because they will have lower repulsion with each other. So if you have to add an extra electron to that configuration in front of us, the new electron is gonna go unpaired to the next orbital rather than going to pair up with the already existing orbital here, because again, that is gonna be much lower in energy because of the less repulsion expected in this case. And if you have to put a second one, it's going to be basically unpaired in the next orbital till you have no choice. If you have to add the fourth one, you will have to pair them up with one of the already existing one because you have no choice. So that rule is going to work only if you have an empty orbital where you can put your electron in an unpaired situation. The importance of the magnetic spin quantum number is how it affects the magnetic properties of substances. Basically, when you have two magnetic moments that are oriented in the same direction, they will add up to each other to an overall magnetic moment for the substance. If you have unpaired electrons, they will actually add up to an overall magnetic moment in the substance. And the substance in this case is going to be called a paramagnetic substance. In comparison to the other situation, if you have all your electrons in the orbitals paired up, they will basically gonna cancel out each other and result in what is called a diamagnetic substance that does not have a magnetic moment at all. So that's the situation if all your electrons are paired up in the orbitals. So let's apply these rules that we just discussed to the electron configuration of a couple of elements. Start with hydrogen. You have only one electron, and again, that electron is going to prefer to go to the lowest energy orbital first. It's very clear that that is going to be the 1s orbital. Then if you move to helium, which has two electrons, the second one still have space to go into the lower energy orbital 1s. So it's going to be two electrons in that orbital or 1s2 configuration, and so on. So we move to the next one, which is lithium, 3 electrons. 2 of them are gonna occupy the 1s orbital, Third one is going to go to the next one in energy, which is 2s orbital. So it's going to be 2s1. And carbon is going to be 1, 2, 1, 2 in 1s and 2s respectively. And then 1, again, according to Horn's rule, that 6 electron is going to go unpaired in one of the empty p orbitals. It's not going to pair up. Oxygen, you will have 2 in the 1s, 2 in the 2s, and then 1, 2, 3. The fourth one has no choice but pairing up with one of the already unpaired electrons in the p orbital. And you keep adding electrons that correspond to the atomic number of the element till you go to the noble gas configuration, which is basically the complete filling of all the orbitals that belong to that corresponding energy level. Again, one note on the magnetism: anything that has completely paired up configuration is going to be expected to be diamagnetic. Anything that has unpaired electrons is going to be expected to be paramagnetic, with a magnetic moment that is directly proportional to the number of unpaired electrons. So the higher the number of unpaired electrons, the stronger the magnetic moment of that substance.